Black holes might just be one of the most fascinating and mysterious phenomena in the universe. They are massive beasts in terms of power, but at the same time virtually invisible to us. A black hole weighing perhaps 2 to 4 million times the mass of the Sun is a prime example. Because of the research that was put into them over the last couple of decades, we've gone from knowing absolutely nothing about them to getting to learn more and more up close and personal. While things have just gotten crazier, Michio just announced that we finally got to look at what's inside a black hole. This new information brings light to the details the world of science might have missed all along. Join us as we dig deeper into black holes and unveil what's inside. Space is big and bad. Before we get into the details of what Michio found, we have to talk about the firsts. Even though most of us have some idea what black holes are, there are still some gaps in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept of black holes was purely theoretical. It took another 50 years for the scientific community to find evidence that black holes actually exist. This happened in the 1960s, when they were studying the Cygnus constellation and noticed an oddly bright blue star emitting X-rays. This star wasn't a stagnant object, but was orbiting around a giant black something. Upon further investigation, it was found that the X-rays weren't just moving around on their own, but were being sucked into the black thing they were orbiting, thus the name black hole. This discovery was significant because it provided proof that black holes actually exist, and that they were not just a figment of Albert Einstein's wild imagination. While that was great, it also meant that there was this unreal entity in space that we urgently needed to know more about. Researchers all around the world got to work. This black hole was named Cygnus X1, and it is located in the constellation Cygnus, about 6,000 light-years from Earth. It was no small discovery. It's about 14 times brighter than the Sun and incredibly dense, which causes it to have a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it is called a black hole. The concept of a black hole is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, never to be seen again. But that aspect of danger makes it even more necessary to learn everything there is to know about them. Was this it, or were we just beginning? The answer ended up being the latter. After the discovery of Cygnus X1, scientists started to search for other black holes. They found that there may be close to over 100 million black holes in the Milky Way alone, but because they are so incredibly hard to detect, we still don't have an exact number. Nevertheless, from the looks of it, there are several million black holes in the Milky Way and our very galaxy, which is what makes them even more important to study. So let's break it down. The main concern with black holes is always going to be gravity. Their gravitational pull is so intense that anything that enters it compresses down astronomically until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners that suck everything in. One of the scariest parts about the research that's gone into black holes is the fact that if someone were to fall into one, they would get stretched to the point that they become a single line. This process would happen slowly, and the person would die before the final form actually sets in. So let's just say that no one should be stepping into one. But they're all over? So could we really be in danger? Despite the fact that the closest black hole to Earth is 500 to 1,000 light-years away, it's still close enough to bring up questions and concerns. In 2021, scientists were able to release the first clear photograph of a black hole, specifically the M87 black hole. This black hole was photographed several nights in a row, and with each photograph, the researchers gathered more and more evidence about it. They had to stitch the individual photos together to create something that filled all the gaps. This way, they were able to figure out that there are 3 layers to a black hole. It's not just one single gaping hole of nothingness, as many people believe. Things are a lot more complicated than that. To even get to the nothingness part of a black hole, you have to make it through the first 2 layers. The first layer is called the event horizon, which is the point of no return. Once you pass the event horizon, there's no turning back, and you will be sucked into the black hole. It only gets worse from there on out. The second layer is the photon sphere, which is the region where light orbits the black hole. Any light that enters this region will be trapped and will not be able to escape the black hole's gravitational pull. Finally, we come to the third layer, which is the singularity. This is where everything that enters the black hole gets compressed down astronomically until it becomes a singularity. The singularity is a point in space-time where the laws of physics as we know them break down, and we just can't predict what happens next. At the singularity, the density is infinite, and the laws of physics as we know them cease to exist. Now, what makes all of this infinitely worse is the fact that every single black hole you study will be entirely different from the last. Sure, they do tend to follow the same 3-layer concept, but the way they function could be vastly different. Now, if this were anything else, all we need to do is hop back on those telescopes and just study the problem at hand in detail. But with black holes, you can't really do that. Scientists can only study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe like the Voyager inside a black hole is not possible because anything that enters the event horizon is pulled towards the singularity, where it is compressed to an infinitely small point. So you can't exactly waste billions of dollars just to get a glimpse every time, because the second the probe gets close enough, it'll just crush into nothingness. Because of that glaring problem, scientists are left with no option but to study these objects in a 2-dimensional way, even though they are 3-dimensional phenomena in reality. To make matters even more challenging, there are also the 2 problems of every black hole being unique and the laws of physics as we know them breaking down when we try to explore the inside. This means that the traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean that the researchers haven't been busy. There are lots of different theories and explanations of black holes, and with each one, things get more and more interesting. One of the most compelling theories about the formation of black holes is that they are created from collapsing stars. When a star exhausts all of its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. As a result, the star begins to collapse in on itself, becoming smaller and denser. If the star is massive enough, this process can continue until it becomes a singularity. To understand the nature of black holes in depth, NASA scientists turned their attention to the core of the galaxy M87. Astronomers observed a super-powerful whirlpool of superhot hydrogen gas that was spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of the spinning disk of gas should have caused it to violently fly apart in all directions, but it didn't. Scientists deduced that there had to be a colossal mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns, and could only be a black hole. But that's not the only theory where black holes spin. In 1963, the New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a spinning black hole. They showed that a spinning black hole wouldn't collapse into a point, as previously thought, but into a ring of fire or a thin disk. The disk would be spinning so rapidly that centrifugal forces would keep it from collapsing. This spinning disk of matter is called the ergosphere, and it is the region surrounding the black hole where the laws of physics start to break down. But the most intriguing feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This theoretical passage through spacetime could connect two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed to oblivion, one would be sucked down a tunnel through the ring of fire and shot out a white hole in a parallel universe. To understand how this works, we need to look at the concept of spacetime. In Einstein's theory, spacetime is the fabric of the universe where objects would mass warp this fabric, creating a gravitational field that causes other objects to move toward them. Now imagine a sheet of paper representing spacetime. If you place 2 points on the paper and draw a line between them, this is a representation of how objects move through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole, a shortcut through spacetime that connects 2 distant points in an instant. Wormholes aren't just a sci-fi concept. They are actually a prediction of general relativity, although they have never been observed. The existence of wormholes has been debated for years, and while they have not yet been proven to exist, the theory that they could be created by spinning black holes is one of the most intriguing ideas in modern physics. But what happens when you get inside a black hole? Is it possible to travel through a wormhole and emerge in a different universe? One of the most famous theoretical physicists of all time, Stephen Hawking, spent much of his career exploring the nature of black holes. He proposed that black holes could be a gateway to other universes, and that they might even serve as a bridge between different dimensions. According to Hawking, if you were to fall into a black hole, you would be crushed to oblivion by the singularity. But instead of being destroyed, you would be transported to another universe where time and space are warped in ways that are beyond our comprehension. Hawking's theory suggests that black holes could be a portal to other dimensions, allowing us to travel to distant parts of the universe in an instant. However, this idea remains purely theoretical, and there is no evidence to support it. One of the biggest mysteries surrounding black holes is what happens to the information that falls into them. According to the laws of physics, information cannot be destroyed, but when something falls into a black hole, it seems to disappear forever. This is known as the information paradox, and it has puzzled scientists for decades. In 2012, physicist Joseph Polchinski proposed a solution to the information paradox known as the firewall hypothesis. According to this theory, there is a ring of fire surrounding the event horizon of a black hole, which would incinerate anything that falls into it. This would prevent any information from being lost, as it would be burned up before it could enter the black hole. But this theory has its problems. If the firewall hypothesis is true, it would violate one of the fundamental principles of quantum mechanics known as the no-cloning theorem. This principle states that it is impossible to create an exact copy of an unknown quantum state. If information is destroyed in a black hole, it would be impossible to retrieve it, and this would violate the no-cloning theorem. So where does that leave us? The truth is, we still don't know what happens inside a black hole. The laws of physics as we know them break down when